welcome. I am Debasish Behera, lecturer in civil engineering. In this video we are going to see one of the topics of structural design 1, that is analysis and design of singly reinforced sections by limit state method. So before moving into the topic, we will just see the basics, that is what is limit state method, what are the types of limit state method, what is design load, what is design strength, and finally after seeing the assumptions in limit state method, we will go to the analysis part. So let us see what is limit state method. It is an acceptable limit for safety and serviceability requirements before failure occurs in a structure. So it is one of the method where we design the structure for safety against collapse, that is by taking ultimate loads and ultimate moments, and finally check for the serviceability requirements. Then if we see the types of limit state, there are two types of limit state. One is limit state of collapse and other is the limit state of serviceability. In limit state of collapse, again we have flexure, shear, compression and torsion, which are the imaginary behavior, and in limit state of serviceability we have deflection, cracking and vibration, which are the real behavior. Then design load. What is design load? Fd is equal to Fck into gamma f, where Fck is the characteristic load. As you might be knowing, characteristic load is the load which has got 95% of probability of not being exceeded during its design life. And Fd is, and design strength Fd is equal to Fck by partial safety factor for materials, where Fck is the characteristic strength, that is the strength below is not more than 5% of test results are expected to fall. So if we look at the partial safety factors, that is we have two partial safety factors. One is for design load and other is for materials. If we see the partial safety factor for loads, for different load combinations we have got different partial safety factors in both the limit state of collapse and in limit state of serviceability, such as for dead load and live load combination. In limit state of collapse we have 1.5 and 1.5. In the other side of limit state of serviceability we have 1 and 1. Similarly for dead load and wind load combination we have got 1.5 and 1.5. In limit state of serviceability again 1 and 1. The material side, in limit state of collapse we have for concrete 1.5 and for steel 1.15, and in limit state of serviceability for concrete 1 and for steel also 1. So if we see, we are multiplying a factor which is greater than 1. So this makes the design load even more higher than the actual load. So here we are overestimating the load, and in the strength side, as we are dividing a factor which is greater than 1, we are underestimating the strength of the structure. So this equation actually makes the structure more safe. But if we go the reverse of it, that is if we underestimate the load and overestimate the strength, then we are calling for failure, right? So next, moving on to the assumptions in limit state of collapse flexure. First assumption is that plane section remains plane before and after bending, that is strain variation is linear. Second is tensile strength of concrete is ignored. Third, as you can see, maximum strain in concrete at the extreme compression fiber is taken as 0.0035, and maximum strain in steel at the time of failure should not be less than 0.87 Fy plus 0.002. Ideal stress strain curve for concrete is rectangular parabolic, that is, as you can see here, parabolic up to a strain of 0.002, and then we have got a linear portion, and the stress is 0.446 Fck. Now this stress, that is 0.446 Fck, is coming. Let us suppose the characteristic strength of concrete be Fck, Now, in practical cases, the structure is actually achieving 67% of the strength that is determined in the laboratory. So we can take it as 0.67 FCK. To this, as I said in the previous slide, to this we are dividing a partial safety factor which is greater than 1. In case of concrete, we are going to divide it by 1.5. So it makes, if we calculate this value, we will get it as 0.446 FCK. Right? Then finally, the last assumption is that partial safety factor for concrete and steel are taken as 1.5 and 1.15, which makes the design stress of steel and concrete as 0.87 Fy and 0.446 Fc. Right, after knowing these assumptions and the previous slide, we will move on to the analysis part. If we see the analysis part, first of all, what is the singly reinforced beam? If the reinforcement is provided in the tension zone, then the beam is said to be a singly reinforced beam. In analysis, we are actually going to determine XU max, XU, the lever arm, and the moment of resistance. XU max is nothing but the maximum depth of neutral axis which we get for a balanced section. Then we need to determine XU, with the help of which we can know whether the beam is a balanced beam or under reinforced beam or a over reinforced beam by comparing it with XU max. Then we have to determine the lever arm, because this lever arm will help us to get the moment of resistance of the section. So let us go one by one. First, let us see the determination of XU max. Suppose this is the cross section of the beam having a width of B and an effective depth of D. This is the strain variation diagram, which is just in the assumption part we studied. The strain in the extreme compression fiber of concrete is 0.0035, and strain in steel at the time of failure should not be less than 0.002 plus 0.87 Fy by Es. Let this be the maximum depth of neutral axis for a balanced section. So this comes out to be, if this is XU max, this is the effective depth, this comes out to be D minus XU max, right? And this is the stress block of concrete, where the maximum stress in concrete is, where the design stress in concrete is 0.446 FCK, and the stress in steel is 0.87 XY. So let us see how to determine this XU max. From this strain diagram, these two triangles are similar triangles, so we can write the equation directly as XU max by 0.0035 is equal to D minus XU max by 0.002 plus 0.87 Fy by Es. So it implies that we can write it as D minus XU max by XU max is equal to 0.002 plus 0.87 Fy by Es whole divided by 0.0035, right? So which makes this XU max gets cancelled, and one we will take it to the right side. So it implies that D by XU max is equal to, one has gone to the right side, so 0.002 plus 0.0035 makes 0.0055 plus 0.87 Fy by Es whole divided by 0.0035. It implies that XU max by D, just taking the reciprocal of it, XU max by D is equal to 0.0035 by 0.0055 plus 0.87 Fy by Es. With the help of this equation, if we know the grade of steel and if we know the effective depth, then easily we can determine XU max, right? Then let's move to determine XU. So determination of XU is actually very easy, because once we know the neutral axis, we know that neutral axis always divides the section into two halves, the compressive part and the tensile part. So the compressive force is always equal to the tensile force. Now to determine the compressive force, we must know the strain values at different points. With the help of strain values at different points, we can determine the compressive force. Let us see how to determine. Now this is the section that we have considered. This is the strain diagram where we can see the maximum strain in concrete as 0.0035, and this is the stress block where the stress in concrete is 0.446 FCK and stress in steel is 0.87 Fy. So let us see first. First let us write XU by H. These two triangles are also similar triangles. So XU by H, we can write it as 0.0035 divided by 0.002, which implies that XU by H is equal to 7 by 4, or we can say that H is equal to 4 by 7 of XU. So we got the point where the parabolic portion changes to linear portion this distance as 4 by 7 of XU. This entire length is XU, out of which this is 4 by 7 XU, so this part will be automatically 3 by 7 of XU. Now to determine the compressive force, we have to multiply this area of stress block to the width of the beam, because if we see the isometric view, this entire stress block is distributed like this through the entire width of beam. That is why to get the compressive force, we need to determine the area of the stress block multiplied by the width of the beam. So to get the area of stress block, we have two parts. First is the rectangular part and below is the parabolic part. So rectangular part area is very simple, 0.446 FCK multiplied by 3 by 7 of XU multiplied by width of the beam plus the area of this parabolic portion. We will take it as 2 by 3 of base into height, that is 2 by 3 into 0.446 FCK into 4 by 7 of XU multiplied by the width of the beam. So if we solve this equation, we will get the answer as 0.36 FCK XU into B. This is the compressive force. Now to get the tensile force, it is very simple. We know the design stress of steel. To this design stress of steel, we need to multiply the area of steel, that is 0.87 Fy into AST. AST is the total area of reinforcement, that is number of steel bars that we have provided into the cross sectional area of each bar. So we got the compressive force and tensile force. Now we will equate both the compressive force and tensile force. After equating, automatically we will get the value of XU. So let us equate compressive force equal to tensile force. It implies that 0.36 FCK xu into b is equal to 0.87 fy st. So from which we get xu is 0.87 fy st by 0.36 into fck into b. So with the help of this equation we can determine the actual depth of neutral axis. After getting actual depth of neutral axis and balancing depth of neutral axis, we can compare both of these and know whether the section is balanced section, under reinforced section or over reinforced section. Next part of analysis, we will determine the lever arm.